Hello everybody and welcome to this A-level chemistry video about shapes of molecules. And in this video we will look at valence shell electron pair repulsion theory. We'll look at the classic shapes that you need to be able to remember for A-level chemistry, and we will look at bond angles and the names of these shapes. We will also look at how lone pairs of electrons in the outer shell can affect the shapes of molecules, and we will look at how you can actually work out the shapes of a molecule, so you don't have to remember everything, you can work a certain number of things out. Then we'll move on to look at ions and how ions are slightly different to uncharged molecules. I'll give you some questions that you can test yourself with, and then I think we'll finish with a few tricky examples that it's worth being a little bit familiar with before you enter your exam. Before you can learn too much about shapes of molecules, it's really important to get to grips with valence shell electron pair repulsion theory, VSEPR for short. Now, VSEPR is obviously concerned with the electrons in the valence shell, and so we need to define them. The valence shell, that is the outer shell, or energy level of course, and the outer shell, that is the shell that is involved in bonding. Now, the next part, electron pair, that makes sense because we know from atomic structure that electrons reside in orbitals where they can fit two electrons into one orbital. And the most important part really of VSEPR is the R, the repulsion, because it's that influences the shapes that molecules can have. Now, remember, electrons are found whizzing around the nuclei. Now, what we haven't really explored too much in atomic structure is the electrons aren't considered to be the dots that we represent them as. What they are considered to be is something called charge clouds. And so the shape of a molecule depends on these clouds of electrons that are moving around a central nucleus. Now, bonding pairs and lone pairs of electrons both exist as charge clouds, and so the charge cloud is an area where you have a large chance of finding an electron, because electrons don't stay still, they're moving around all over the place, inside their orbital or inside their region where they're located in a bond. And so pairs of electrons in bonds are more likely to be found in certain places. And when you draw a bond as a cloud, you show it not as a regular rectangle, but you show it with slightly fatter region in the middle where the electrons are more likely to be, and it tapers away to a point at both ends where the electrons have got far less chance of being. And that's what we mean by charge clouds. Now, what's important for VSEPR, though, is not how we draw the electrons in a bond, but it's how the electrons interact with each other. Remember, electrons are all negatively charged, so these charge clouds are going to repel each other, and that's crucial point number one. And they repel each other until they are as far apart as possible in three-dimensional space. And that's really significant because once these charge clouds are as far apart as possible, the repulsion that they're experiencing is at its minimum, and so they are the most stable of all. Okay, so let's sum that up. VSEPR, electron pairs repel each other until they are as far apart as possible in three-dimensional space. And so what this becomes is, well, how many electron pairs are there and where will they repel each other to in three-dimensional space? There's a little bit more about this later, about lone pairs of electrons, but for now I think that's enough for us to dive in. The first thing to note about drawing molecules is that they are three-dimensional structures most of the time. And so when we've been drawing molecules at GCSE level before now, we always draw them in 2 dimensions. Whether we're drawing the dot and cross diagrams or whether we're drawing the sticks, we are representing molecules as being in 2 dimensions. Whereas in fact, as I say, most of them are 3-dimensional shapes. And so the rules for drawing shapes in 3 dimensions are such that you have to be really careful about how you actually draw the bonds. That's the crucial thing, because there's 3 types of bonds to draw. The first type of bond is the classic stick, which is what you've drawn already, and what that means is the atoms that are in the bond are in the same plane, so they literally are one straight line away from each other in the flat of your paper. The next type of line is a solid wedge, And this is representing a line coming out towards us, which is why it's fatter at the end closest to us. And that shows a bond that is projecting out of the paper towards us in 3 dimensions. And then the final type of bond is sort of like a broken line, and that's showing a bond that is moving away from us, sort of into the paper, deep into the paper, or into your desk, or however you want to think about it. But this bond is definitely in a different plane to the other two. And when you put them all together, you get a shape where some of the bonds will be in the flat of the paper, and some of the other bonds will be coming out towards you or going into your paper, depending on how you've drawn them. And it's really important, if you've been asked to draw a shape that is 3-dimensional, that you use the wedges and the broken lines. The precise nature of the broken line is a bit flexible. If you don't want to put any kind of perspective on that at all, that's okay. You can just draw 4 or 5 dashed lines like this and have it looking effectively like a dashed rectangle. They don't have to taper away to a point in the distance. That's okay. Now, there are 5 classic shapes that you need to remember. You need to be able to recognise them, and you need to be quite quick at assigning a name for the shape and a bond angle to them. And these shapes depend on how many pairs of electrons there are around the central atom. And so if we just work through these, and we won't give any identities to the elements at first, we'll just use A for the central atom and B for the bonded ones around the outside. So in the first example, we've got a formula AB2. So that means there are 2 atoms of B around the centre of atom A. And so there will be 2 bonds between A and B, and there will therefore be 2 charge clouds of electrons around A. These charge clouds repel each other, so they are as far apart as possible in 3-dimensional space. And 360 degrees is 3-dimensional space. And so if we've got 2 things as far apart as possible as those 2 things can be, is 180 degrees. So this molecule would have a linear shape, and those pairs of electrons are as far apart as they can possibly be, 180 degrees. If we move on to a different formula, AB3, this time, because there are 3 bonding atoms, there will be 3 charge clouds, and they repel each other, so they are as far apart as possible in 3-dimensional space, and this time it is 120 degrees, and that is 360 divided by 3. And so this gives us a different shape that we're showing here, and this is called a trigonal planar shape. And planar means it is flat. It is all in one plane, the plane of our paper. That's how we draw it. So no perspective is needed, no wedges or dashes for either of these first 2. The third one, though, does start to need it. And this is when we've got 4 pairs of electrons and we've got 4 atoms bonded to a central atom. And this, we would be forgiven for thinking it would be 90 degrees, because 360 divided by 4 is 90 degrees. That's how far apart they could get in 2-dimensional space. But 3-dimensional space is a bit more complicated, and we can actually get 109.5 degrees apart when the bonds are pushed upwards and downwards, so out towards us and into the paper. And this is actually exactly the same shape that I showed you on the previous page. This is the tetrahedral shape, or you would call it a tetrahedron, because you've got 4 corners to this 3-dimensional shape. And so that's for 4 pairs of electrons. If we move on to 5 pairs of electrons, we have got the AB5, and so we've got 5 pairs of electrons. Now we're definitely in 3 dimensions, and this forms a trigonal bipyramid. And what that means is we've got a trigonal-based pyramid, and then we've got another pyramid sort of below it as well. So that's why it's bipyramidal. There's one pyramid pointing upwards and one pyramid pointing downwards, and their bases are kind of on top of each other, and so that's why it's a bipyramid. And so the bond angles for these, well, there's actually 2. There's these atoms here, which are referred to as equatorial, like the equator of the Earth, and the bond angle between them is 120 degrees. Then we've got these axial atoms here, and the bond angle between the axial bond and the equatorial bond is 90 degrees. So there's 2 bonds there. That's actually the only one where there are 2 different bond angles. And then the final sort of analogue, the final shape to remember, is when there are 6 pairs of electrons around the central atom. And this one is complicated to draw, but it's actually quite easy in all other respects because it's just got the name octahedral, which I'll explain in a minute, and all the bond angles are 90 degrees. So it's complicated to draw because what you've got is you've kind of got 2 square-based pyramids on top of each other. So it's a bit like the previous one, only we call it octahedral. And so we've got 2 bonds projecting out towards us, 2 bonds projecting into the paper, and then those are the equatorial bonds. And then we've got the axial bonds above and below. And so it's octahedral because it's got 8 sides to it, like a diamond, so 8 faces. So this is the octahedral shape, 90-degree bond angle in all cases. So those were all the sort of like analogues of the 5 basic shapes. Now let's personalise it to some that are really commonly occurring on exam questions, and some of them are even named on your specification. So for 2 pairs of electrons, there is beryllium chloride, which has got 1 beryllium atom and 2 chlorine atoms. And this is the linear arrangement, 180-degree angle. I'd like you to note actually that the BCl2 doesn't have a full 8 electrons. It's actually only got 4 electrons in beryllium's outer shell. And that's the same for the next one, BF3, boron trifluoride. That's only got 6 electrons in its outer shell. This is the trigonal planar, the flat triangle arrangement, 120-degree bond angle. And methane is the most common with 4 pairs of electrons. We've already seen that once already. And for 5 electrons, PCl5 is the most common example, with the triangle in the middle, the equatorial atoms having a bond angle of 120, and the equatorial to axial bond angle being 90, the trigonal bipyramid, or trigonal bipyramidal, they're both fine. And for the 6 pairs of electrons, SF6 is by far the most common, sulfur hexafluoride, and that has a bond angle of 90 degrees and looks like this. I strongly recommend you practice drawing, particularly the octahedral, but also the trigonal bipyramid as well, like phosphorus pentachloride. Let's return now to something I mentioned earlier, which is lone pairs of electrons. Now, some molecules have got pairs of electrons in their outer shell that aren't involved in bonding. They're not part of a covalent bond. Now, crucially, these lone pairs of electrons do affect the shape of a molecule. So you need to watch out on dot and cross diagrams to see if a molecule has got a lone pair of electrons, or the method that I'm about to show you for working out the shape of a molecule, you need to account for lone pairs there. And the significance of a lone pair of electrons, other than affecting the shape, is actually you don't account for it when you name the molecule. And so what's funny about that is that the electrons have got some repulsion, but they don't really take up very much space because electrons are absolutely tiny compared to an atom overall. So the electron repulsion is really significant and you need to account for it. Now this links back to VSEPR, to the repulsion between clouds of electrons, because lone pairs of electrons are a bit more compact. They're not spread between 2 atoms, they're localised on 1 atom, and so they're not the stretched out shape that a bond is, they're more bunched up, sort of pear-shaped orbitals where you find the electrons very close to a central atom. And so because of this, the lone pair has got a slightly greater charge density than a bonding pair of electrons. And so the experience of repulsion for nearby clouds is slightly greater because the more concentrated charge from this lone pair. And so the VSEPR states that the repulsion between 2 bonding pairs is slightly less than the repulsion between a bonding pair and a lone pair, and that is slightly less than the repulsion experienced between 2 lone pairs of electrons. And so 2 lone pairs of electrons have got greater repulsion than anything else. And so the effect that that has on actually molecules is that if a molecule contains a lone pair, the bonding pairs of electrons will be squeezed closer together by approximately 2.5 degrees. And if there are 2 lone pairs of electrons in a molecule, then the bonding pairs will be squeezed together by 5 degrees, 2 lots of 2.5 degrees. So that 2.5 is an important number to remember. Let's have a look at 2 examples of this on the next page. So the 2 examples to remember are ammonia and water. And what's really important is that both of these have got analogues that don't have lone pairs. So ammonia has got 4 clouds of electrons around it, 3 bonding pairs and 1 lone pair. So in essence it is like the tetrahedral shape of methane. However, because one of these charged clouds is a lone pair of electrons, the 3 remaining bonding pairs get squeezed closer together, and so instead of the bond angle being 109.5 degrees, the bond angle is actually 107. And instead of us calling this a tetrahedral shape, because we've lost the top atom in our tetrahedron, it's not a tetrahedral shape anymore, and we call this a pyramidal shape. And that's the case for ammonia and any other sort of analogue of this where you've got 3 bonding pairs and 1 lone pair. It will be this pyramidal shape with 107 degrees. Water is similar because it also has got 4 clouds of electrons, only this time there are 2 bonding pairs and 2 lone pairs of electrons. And so in the same way as for ammonia, the lone pairs have got greater repulsion, so they squeeze the bonding pairs closer together by 2.5 for each lone pair. So we start with our semi-tetrahedral appearance, and then we take away 1 bond and replace it with a lone pair. That squeezes the bond pairs 2.5 closer, and then we take away another one and we squeeze it a further 2.5 closer. So it's a total of 5 degrees closer, so the bond angle in water is 104.5 degrees. And that will be the case for, again, anything similar to water. So H2S is like water, H2O, except we've got sulfur instead of the oxygen, and we'd have the exact same situation in terms of bond angles and the shape, which is most commonly called V-shaped, but you do see other names such as bent line or non-linear, but I think V-shape is the best name. We've been looking at molecules that don't have any charge, but if we look now at molecular ions, the picture gets a little bit more complicated, but not much. So if you consider something like NH4+, and what this means is we've got a central nitrogen atom and we've got 4 hydrogen atoms bonded to it, and there is an overall charge of positive. Now, remember, ions are charged particles because they have either lost or gained electrons. And if something is positive, they have lost 1 electron. And so what that means is nitrogen, which previously had 5 electrons, has now got 4, and it uses those 4 to form 4 bonds to the hydrogen. And so what looked really complicated is actually not, because NH4 is actually a tetrahedral shape, NH4+, I should say. And then similarly, if we looked at NH2-, well, nitrogen's normally got 5 electrons because it's in group 5. It's gained 1 electron because the whole particle is negatively charged, and we've got 2 covalent bonds to hydrogen. So what we've actually got now is we've got 2 bonding pairs of electrons, and we've got 2 lone pairs of electrons. And so this is exactly like water. So NH2- is going to be the same shape as water, the V-shaped, and it's going to have a bond angle of 104.5. And so molecular ions have got the same shape types as when you've just got regular molecules. There's just an extra level of complexity because either electrons have been taken away or they've been added. So drawing a dot and cross diagram might be helpful to work out how many bonding pairs and lone pairs there are, but I'm going to show you another method now that I think is easier than working out the dot and cross diagrams, and it's the method that I suggest that you use. For all of these molecules that we've been looking at, there has always been what you would call a central atom. And the rules for working out what something's shape is, you need to find out what group the central atom is in the periodic table. And that's significant because that will tell us how many valence electrons that atom has got. Because if something's in group 5, it's got 5 valence electrons. And then the next step is to work out how many atoms are bonded to the central atom. What is the coordination number, is the fancy way of saying that. Because typically each bonded atom will bring an extra 1 electron to the whole bonding structure within the molecule. And then we need to look at the overall charge of the molecule and take that into account, because if something is positive, we need to take away an electron, and if something is negative, we need to add an electron, or more than 1 electron if something is 2+ or 3+ or 3-, etc. And then that, when we add all those three numbers together, will give us our total number of electrons that are involved in bonding or in the valence shell of the central atom. And then we need to divide this number by 2, because electrons always go around in pairs, and this tells us how many electron pairs there are around the central atom. Then we need to compare the number of electron pairs to the number of bonds. And if those numbers are identical, then all the electron pairs are involved in bonding, and so there are no lone pairs. But if this number is greater than the number of bonding pairs, then that means that the difference is how many electrons are in lone pairs, or how many pairs of lone pairs there are. So let's look at an example. Let's look at those two that I just showed you on the previous page, NH4 plus and NH2 minus. How did I know what shapes they would be? Well, nitrogen is in group 5, and so for both of these, we put 5 for step 1. In NH4 plus, there are 4 atoms bonded to the nitrogen, so we put a 4 here. In NH2 minus, there are 2 hydrogens, so we put a 2 there. In terms of the charge, NH4 plus has lost an electron, so we put -1. NH2 minus has gained an electron, so we put +1. We add all of these together, and so 5 plus 4 take away 1 makes 8. 5 plus 2 add 1 makes 8 as well. So they've both got a total of 8 electrons. When we divide them by 2, of course, that means that they will both have 4 pairs of electrons. And then for NH4 plus, when we track back to the number of bonds, we've got 4, so that means these are all bonding pairs. Whereas for NH2 minus, we find we've only got 2 bonding pairs, and that must mean that there will be 2 lone pairs. And then the final step from here is to draw the structures of those 2 shapes. I'd like you to have a look at these for yourself. You can work out what these shapes would be, and then try drawing them, naming them, and working out the bond angle now. So pause it, and then I will reveal the answers in a moment. Okay, so here are the answers popping up. SiH4 is tetrahedral with a bond angle of 109.5. NF3 is just like NH3, so it's pyramidal with a 107-degree bond angle. BF4 is also tetrahedral because normally B has only got 3 electrons, so we've got 8, so this is tetrahedral, 109.5. H3O plus, that is like ammonia as well, so that's pyramidal, 107 degrees, and PF4 minus is like trigonal bipyramidal, but we've lost one of the bonds and it's become a lone pair. To be honest, you would be able to replace any of the bonding pairs with a lone pair here. You wouldn't be expected to name this shape either. But you would be expected to speculate that the presence of the lone pair in this position would squeeze the bonding pairs closer together, and so the bond angle between the axial and the equatorial probably wouldn't be 90 degrees anymore. It'd probably be 87.5. And the bond angle between the other equatorial atoms would probably not be 120 anymore. It's likely to be 117.5 as well, because the atoms got squeezed closer together. The bonding pairs of electrons specifically got squeezed closer together. I think leading on from that, it's a good opportunity to look at the slightly more complicated situations where bonding pairs of electrons are replaced with lone pairs. And that leads to 3 complicated sounding names, or at least weird sounding names, and weird corresponding shapes. The good news is, I think the questions where you have been asked to name these shapes are very old questions from more than 10 years ago, so I don't think you're likely to be asked to name these on an exam, but I'm using them just in case. And also, I don't think you need to be able to justify why they are the shape they are. Particularly T-shape is a little bit weird. So the seesaw arrangement is what you get when you've got trigonal bipyramidal and you take away 1 pair of electrons. Now, I called that a trigonal pyramid previously, but actually we could have taken away the top pair of electrons like I did on the previous page, but actually it's slightly more stable if we take away one of the equatorial atoms, which leaves us with this seesaw looking shape. Now, it's called a seesaw shape because if you tilt your head on its side or you rotate your page or something like that, the ones that I've drawn as wedges and dashes, that becomes kind of like the pivot of a seesaw. So that's why it's called a seesaw shape. And so this reduces the bond angle between the axial and equatorial to something like 87.5, and we get a shape that looks more like a seesaw. But like I say, the good news is they're not likely to be too fussy about which one you take away, but the equatorial is probably more likely. Then the T-shape is very logical in terms of its name. If we take away the two equatorial that have been drawn in 3 dimensions, so as a wedge and as a dash, we end up with 3 bonds that are all in the same plane as each other and 2 lone pairs just off to the side on the equatorial position. And this has the effect of repelling the bonds closer together. Now, what's a little bit funny about this is that the repulsion is not quite so great. The angle is still probably about 87.5. And the reason for that is that there is repulsion from above and from below. And whilst they're not cancelling each other out totally, they are reducing the impact that they have. So that's the T-shaped molecule. Now, you don't need to know why you get the T-shaped molecule rather than the corresponding trigonal planar shape, which you'd get if you took away the 2 axial bonds. Suffice to say, if you did want an explanation, a very brief one is that the combined repulsion between lone pairs and bonding pairs is greater for the trigonal planar shape because you've got 6 repulsions between bonding pairs and lone pairs at 90 degrees, and that's greater than all the others. And so that's the reason. And the reason I make a point of saying that is that the square planar shape is for the octahedral arrangement when you take away the 2 axial bonds. And so xenon tetrafluoride is the example that I've got here, and we've got a lone pair above and a lone pair below. So we've actually, even though we draw it in 3 dimensions with the wedges and the dashes, it's a flat molecule with the lone pairs above it and below it, but we show it in perspective to allow us to visualize the lone pair's position more clearly. And so this is more stable than the corresponding taking away 2 atoms on the side, because the lone pairs are 180 degrees apart, whereas if we'd put them on one side, they'd be 90 degrees apart. And so that's really, really close. And so it's much more stable for the lone pairs to be above and below the molecule than it is to be off on one side together 90 degrees apart. And that's in contrast to the T-shaped molecule, where the lone pairs are still 120 degrees apart, a little bit more in fact once the extra repulsion is taken into account. So that is slightly different justification. So I would suggest to you, remember how to draw these shapes, remember the bond angles and their rules, but don't worry too much about how you name the shapes. And just to go back to the square planar, I've labelled it as a 90-degree bond angle, and that's because the lone pair above is pushing the bonds downwards, the lone pair below is pushing the bonds upwards, and those effects exactly cancel each other out, so the bond angle is still 90 degrees. You can get some molecules that are a little bit awkward because they contain double bonds. Now, a classic example is something like carbon dioxide or sulfur dioxide, sulfur trioxide, and probably the method that I would recommend there is to actually work out what the dot and cross diagram is first. Now, you probably will remember that carbon dioxide is linear, and so this is its shape here, 180-degree bond angle. And that's because it's got 2 double bonds, one for each of the oxygens that the carbon is bonded to. And so what's really important to realise here is that the double bonds are treated in the same way as single bonds, as being electron clouds. Yes, there's more electrons in there, but the additional repulsion is not as significant as you might think. And that's because of the nature of the pi bond around the double bond. And so, once you've worked out what the electron sharing is in terms of dot and cross, you can work out, okay, carbon dioxide, 2 clouds of electrons, 180 degrees. Sulfur dioxide's different because remember sulfur's in group 6 and carbon's in group 4. So sulfur's got 6 electrons and the oxygens have also got 6. So we end up with a situation where we've got 2 double bonds between the sulfur and each oxygen, and we've got a lone pair of electrons around sulfur dioxide. So now we know that, well, it's 3 clouds of electrons. And so this is essentially a trigonal planar shape, However, remember that the lone pair causes the shape but doesn't get included in the name. So this is effectively a V shape, or that non-linear shape that is the same as water. Not quite the same bond angle, it's going to be 117.5 because remember in water there's 4 clouds of electrons and 2 lone pairs, but we could still call this a V shape. I thought I'd finish this video by sharing with you a revision aid that I've made for my students. And so how this works is along the top you've got the numbers of pairs of electrons or electron clouds that a molecule might have. And as we go down, we look at what the shapes will be. And so this first row is if for all of the atoms have only got bonding pairs. So we've got the linear, the trigonal planar, the tetrahedral, trigonal, bipyramidal, and octahedral that we've already talked about. And then if we introduce one lone pair, we reduce the bond angle by 2.5 to get us our V shape or our trigonal pyramid or the seesaw that we've just been talking about. And then we've got this one, which is a square pyramid. I've not mentioned this, but we've just taken away one of the axial atoms and replaced that pair with being a lone pair. And then we've got 2 lone pairs, which is the V shape like water, the T shape that we've already discussed, and the square planar that we've already discussed as well, like xenon tetrafluoride. And one last reminder in here, when we are working out shapes, we ignore lone pairs when we name their shapes, but their effects are all important. Remember, they squeeze the bond angle 2.5 degrees closer together. So we don't account for them over here in terms of naming the shape. We just describe it as a V for those bonds and the shape that that kind of makes. Okay, that's the end of this video about shapes of molecules. I hope it was interesting. I'll see you again soon. We'll do something about intermolecular forces. I'll see you then.